Hi, welcome back. Today we're going to be proving an important result, which is called quadratic reciprocity's law. But first we have to state some lemmas that might help us to get to this result. This lemma seems kind of cumbersome, but I just decided to write this more explicitly in order to understand what it's going on right over here. So we have Gauss's lemma, which says the following. We still suppose that P is an odd prime and A is some number such that it's not divisible by P. Now the next step, we just take numbers A, 2A, 3A, all the way up to P minus 1 over 2A. And then we take each number and divide them by P. So this is going to be like you take JA, where J is between 1 and P minus 1 over 2, and just write as P times, I don't know, another multiple, plus some remainder here. And we will take from this list only those numbers such that the remainders are strictly bigger than P over 2. And the total amount of those numbers will be denoted by n. Then Gauss's lemma says that the following Legendre symbol A modulo P is going to be equal to -1 raised to the power of n. There are many notes I should mention while dividing each of those numbers by P, but I will discuss them throughout the proof. So as I mentioned before, we take each number from here and divide them by P. Each of those will produce their remainders, and we're gonna collect all those remainders and construct this set. R1, R2 up to Rn, S1, S2 up to Sm. So this is the set of all remainders after this procedure from this lemma. Recall that if you divide each number by P, you get remainder Rj, which is going to be between 0, and we can include 0, and strictly less than P. Well, I said we can, but at this stage, we actually never get 0. So the remainder will be strictly between 0 and P according to given numbers. Because if we assume that the remainder is equal to 0, then this number JA, so JA is from this list, is going to be equal to Q times P. So it means that this prime, it divides this number JA. However, we know that P cannot divide A, so therefore, since P is prime, then P must divide J. And J is a number between 1 and P minus 1 over 2. And this is not possible. So therefore, when we take all remainders from here, we will never get 0. The remainder is strictly between 0 and prime. And here, this decomposes into two possibilities. Either Rj is going to be strictly less than P over 2, or it can be strictly bigger than P over 2. It cannot be exactly P over 2 just because P is an odd prime. P over 2 will not be an integer. So this set contains the following. R1, Rn are going to be remainders strictly bigger than P over 2, and the total amount of them is n, according how we defined this number n from this lemma. And also the rest remainders S1 and Sm are going to be remainders strictly less than P over 2. The total amount of elements right here is going to be P minus 1 over 2. So this is just exactly n plus m, since we had P minus 1 over 2 elements right over here. Now I see that those numbers are strictly less than P over 2. But now I would like to do some modification in order to make those numbers also strictly less than P over 2. The modification here is straightforward. You just take P and subtract R1, then R2, and then Rn. And those numbers are going to be also strictly less than P over 2. And we just add S1, Sm, those are strictly less than P over 2. And thus, this is a set of numbers strictly less than P over 2 and strictly bigger than 0. And the total amount here is P minus 1 over 2. Turns out, if I rearrange those elements in the natural order, then I will get this is going to be the same as the set of those numbers 1, 2, 3 all the way up to p minus 1 over 2. This is my main claim, but first, in order to show this, I have to prove that if I take any two numbers from this set, they are going to be different. First of all, I'm gonna take some numbers from this part of the list. So I take two numbers from here, and I suppose that p minus rj is equal to p minus ry with different j and I, so with different those remainders. Well, obviously this means that those remainders are equal. Then what we need to recall that what are those remainders? So how can I get this remainder rj? I can get this by dividing element ga. Ga is from this list, and we divide this by p and get that this is just p times q prime, for instance, plus this remainder rj. Likewise, how can I get this remainder ri? I just take element ia. This element again goes from this list. This is just q prime times p plus this remainder ri. And now what I will do here is just subtract both equations. This leads to the following equation. So I just factored out a, and I'll get j minus I, which is equal to p times this bracket q prime minus q double prime. And those remainders, they cancel each other since they are equal. So this equation implies that p divides j minus I times a. However, we do know that p does not divide a, and p is prime. So therefore, we immediately get that p divides j minus I. So it means that j minus I is congruent to 0 modulo p, or j is congruent to I modulo p. However, we know that j and I are such numbers between 1 and p minus 1 over 2. But if I subtract them, so I get j minus I, this is going to be between p minus 1 over 2 minus 1 and the same number with a negative sign. And this is divisible by p. So the only possibility here is when j minus I is actually 0. So it means that j equals I. So it means that we took remainders with different indices and we get those indices must be the same. So it means that with different indices, we get different remainders. Thus, elements p minus j and p minus ri are not equal. So if you take any two numbers from this part of the list, those are different numbers. Similarly, if you take any two elements sj, si, so I mean I take any two elements from this part of the set, then you can prove in the same way that those indices must be equal. So if we have different indices, then remainders have to be different as well. So we know those elements are pairwise different, those elements are pairwise different, but if I take one element here and another element here, will they be different? We have to find out right here. So we just suppose that I take element of the form p minus rj, and I assume this is equal to some si here. This equation implies that if I put rj on the right hand side, I will get rj plus si, which is just p, but in the world of modulo p, this is 0, so this element is congruent to 0 modulo. And now let me just write down two equations where those remainders are involved. So we get those remainders rj si after dividing element of the form ja by p and ia by p as well. So now we have the following equation, and just go to the world of modulo p and rewrite this as ja is congruent to this remainder rj modulo p, and similarly this remainder si is congruent to ia modulo p. And now we go back to this equation and substitute those remainders with those elements. We get that ja plus ia is going to be congruent to 0 modulo. And now since we know that p does not divide a, and here we can just factor this a, and we get that this is going to be j plus I times a, then we can reduce both sides by a, leading to this equation. J plus I is congruent to 0 modulo p. And now it's time to recall that j is between 1 and p minus 1 over 2, and similarly goes to this index I. Now, if I add those inequalities, I'll get that j plus I has to be between 2 and p minus 1. But we know that g plus I is congruent to 0 modulo p, so this is a number 0, p, 2p, negative p, and so on and so forth. But this number j plus I is squeezed between 2 and p minus 1. And we cannot find neither p, nor 2p, nor 0, nor negative p. So therefore, we reached to a contradiction. So we assume that those elements are equal, and we reached to the following contradiction right over here. So let's make a small conclusion. This set has all different elements each other, and those are p minus 1 over 2 elements in total, so we can rearrange them in a natural order, and we get that this set is just nothing but 1, 2, all the way up to p minus 1 over 2. The last step is just I will multiply all these numbers and see what we'll get. Multiplying those elements 1, 2 up to p minus 1 over 2 is the same as just multiplying those elements, because those sets are equal. So we just substitute this product into the product of those elements. Now let's go to the world of modulo p. So let me just write down modulo p right here, and let's notice that this element p minus r1, this is going to be congruent to negative r1, then p minus r2 is congruent to negative r2, and this last bracket p minus rn is congruent to negative rn modulo p. So each bracket will be substituted to negative r1 times negative r2 times negative rn. And then s1 times sm, those will be the same because those remainders are between 0 and p over 2. Now let's rewrite this equation a little bit. So first of all, we have n minus signs, so this is just negative 1 raised to the power of n, and then we multiply all remainders what we have here. Recall that each r you can get from dividing element ka by p. This ka belongs to the family of those numbers. Just recall this. And now, after dividing this by p, we get that ka is equal to this q times p plus rk, but in the world of modulo p, this rk is just the same as k times a. Likewise, you can substitute each rk by sk, and then sk is going to be also congruent to ka modulo p. Now, since those remainders are remainders after dividing a to a all the way up to p minus 1 over 2a, and each remainder is congruent to one of those elements, so it means that the following product is going to be congruent to a times 2a times p minus 1 over 2a, and I should not forget this negative 1 raised to the power of n right over here. This product can be rewritten in the following way, so this is going to be just, well, negative 1 raised to the power of n. We have a times a p minus 1 over 2a's. So this is going to be a raised to the power of p minus 1 over 2 times, well then, product 1, 2 up to p minus 1 over 2. So totally we have the following equation. So if we multiply 1 to p minus 1 over 2, this is the same as negative 1 raised to the power of n, a raised to the power of p minus 1 over 2 times the same product modulo p. Now we know that each number from this list is co-prime with p. So it means that I can reduce 1 from both sides. I can reduce 2 from both sides, and I can also reduce p minus 1 over 2 from the both sides. So I can just reduce the whole product from the both sides. And this leads to the following equation. 1 is congruent to negative 1 raised to the power of n times a raised to the power of p minus 1 over 2 modulo p. Now if I multiply both sides by negative 1 raised to the power of n, I'll get that negative 1 raised to the power of n on the left hand side is congruent to. Now here I'll have negative 1 raised to the power of 2n, which is exactly 1, and I'm only left with a raised to the power of p minus 1 over 2. However, recall Euler's criterion right now. It says that this object a raised to the power of p minus 1 over 2 is the same as Legendre symbol of a modulo p. So this in the world of modulo p. And look, we get that this Legendre symbol is congruent to -1 raised to the power of n modulo p. But similarly, instead of congruent, you can just write down equals. So Legendre symbol a modulo p equals -1 raised to the power of n. If you don't know how this implication holds, just watch previous videos where I explained in the similar manner. Now let's see what we received. Actually, this is the result what we needed. We needed to show that this Legendre symbol is -1 raised to the power of n. This is what we get, and this is what we needed to show. The next lemma is a sort of a sequence of the previous Gauss's lemma. We again suppose that p is an odd prime number, and again a is a number such that it's not divisible by p, but this time we have to include an extra condition. This a is going to be an odd number. Then this Legendre symbol a modulo p can be evaluated as -1 raised to the power of t, where this t can be computed as the sum of the following elements. Well, at first glance, it doesn't make any sense, but again, let's go back to Gauss's lemma, recall what we did, and this will make much more sense. What we did in Gauss's lemma, we took all elements of the form a to a3a all the way up to p minus 1 over 2a. In each of those, we divided by p. So I just take any ja from this list, which is just p times some multiple q, plus some remainder, which we know that this remainder is strictly between 0 and p. Now, in fact, this multiple q is just nothing but this integer part ja divided by p. So this t means that we just collect all those integer parts after dividing each element by p, and we just sum them from 1 to p minus 1 over 2. I hope it's now much more clear. So I'm gonna consider the same set of remainders after dividing a to a all the way up to p minus 1 over a over 2 by p. So those are remainders, and I denote R1, Rn as remainders bigger than p over 2, and S1, Sm, those are remainders strictly less than p over 2. And after dividing each number from this list by p, so ja comes from this list, after dividing by p, we get that this is p times this multiple integer part ja over p plus remainder tj. This tj comes from this set, so it's either one of r's or one of s's. Since this j runs through 1 to p minus 1 over 2, so I have list of elements a to a, p minus 1 over 2a, and they are equal to something. What I do, I'm gonna sum those equations. So I just write a plus 2a plus p minus 1 over 2a. So I just write down this sum j times a. And let's see what we can achieve here. So this object can be written as sum of those elements, multiple this integer part times p, plus sum of all remainders tj right here. Well, here I can simplify a little bit, just I can take this p and factor out from this sum. So this is just going to be p times this sum plus another sum of those remainders. Now this sum of remainders, of all possible remainders, I can just split this sum into sum of remainders strictly bigger than p over 2 and sum of remainders strictly less than p over 2, well, according to this list. Recall that in Gauss's lemma we took p and subtracted each remainder from this list, and then we constructed the following set: p minus r1, p minus rn, s1 and sm, and we proved in this lemma that this set is the same as the set of numbers 1, 2, 3 all the way up to p minus 1 over 2. Now let me just sum these numbers, so 1 plus 2 plus p minus 1 over 2. This shortly can be written as this sum over j running from 1 to p minus 1 over 2. Now, if you sum those elements, it's the same as summing those elements. So this object can be written as summing elements of the form p minus ri, so we just sum those elements, and also we have to add the sum of those elements sk. This can be rewritten a little bit, so sum of p minus sum of ri and sum of p from 1 to n, it means that we have n copies of p, minus this sum of remainders ri plus sum of remainders sk. So far I have those two equations from preceding steps, and now what I want to do, I'm gonna take this equation and subtract this equation in order to get rid of this object. So let's just subtract them. The left hand side is sum of ja minus sum of this j, which is the same as the sum a minus 1 times j if you combine those sums, and this is the same as sum of j times this multiple a minus 1 if you factor this out. So this is our left hand side after subtracting. Now let's subtract right hand side. So as you know, this will be cancelled, and we get this one plus this one minus np and minus this sum. So this is just plus the same sum. Right hand side can be rewritten a little bit cleaner. So we had two of those elements, so this is going to be twice sum of those remainders ri. This equation looks a little bit messy, but this will be simplified immediately if we go to the world of modulo 2. Now, if we are in modulo 2, we can see that this 2 times the sum will be vanished. And finally, this left hand side is going to be vanished as well, since we assumed from the beginning that a is an odd number. So a minus 1 is supposed to be an even number, and an even number is congruent to 0 in the world of modulo 2. So it means that p times this sum minus np is going to be congruent to 0 modulo 2. And now let's simplify again the right hand side of the equation. We have to recall that I denoted this object, so this is the sum of all integer parts, ja over p. So I denoted this right here with the letter t. So this leads to the following equation. So 0 is congruent to p times t minus n modulo 2. And now since p is an odd prime, so it's co-prime with 2, then this means that I can reduce both sides of the equation by p, leading to 0 is congruent to t minus n modulo 2. So this means that t is congruent to n modulo 2. This means that t and n must have the same parity. So it means that if t is odd, then n is odd. If t is even, then n is even as well. This means actually that negative 1 raised to the power of t is the same as negative 1 raised to the power of n. And now let's recall Gauss's lemma, which says that Legendre symbol of a modulo p is negative 1 raised to the power of n. However, we know that this is the same as negative 1 raised to the power of t, and that's what we needed to prove. Now the final big boss, what we've been waiting for, and that is the law of quadratic reciprocity. It states the following: if you take any two different odd primes p and q, then you have this relationship. The Legendre symbol of p modulo q times the Legendre symbol of q modulo p is the same as negative 1 raised to the power of p minus 1 over 2 times q minus 1 over 2. Now this theorem is super vital for us because it helps us to compute Legendre symbol in another way. So if you, for example, have Legendre symbol 3 modulo 101 and you need to compute this, then you can use this relationship in order to flip this fraction, and instead you can compute this Legendre symbol 101 modulo 3, which is much simpler. So that's the main motivation why we really need this law. Now, I have to admit that this proof is not mine, and this is not the first video you will ever see the following proof, but it has so much inspiration for me, so I just decided to repeat this proof, but trying to explain this maybe in detail or in other ways. So the first step here, we're gonna construct on xy plane a rectangle with the following vertices: 0, 0, p over 2, 0, 0, q over 2, and finally p over 2, q over 2 right here. Now, after we constructed this shape, this rectangle, now we're gonna fill this shape with those tiny black bullets. So those are points whose coordinates are going to be integers. And since those coordinates are integers, you have to note that neither of those points, of those bullets, lie on this edge or on this edge, because recall that q over 2 is not an integer because q is an odd prime number. And this edge is constructed with the height q over 2. So neither of those points will be here. Likewise with this edge. So it has width p over 2, and p over 2 is not an integer because p is an odd prime number. The third one, and the most, I think, important one, is we're gonna construct this straight line y equals q over p times x. And if you plug x equals 0, y is going to be 0, so it starts from this point. And if x is equal to p over 2, then y equals q over 2, so the second point is here. So this blue line corresponds to the following equation: y equals q over p times x. So this is nothing but a diagonal of a constructed rectangle right here. And now here I deliberately drew those black bullets so tiny, and line as well tiny, because you can notice here that this blue straight line does not intersect neither of those bullets. This is clearly seen on this picture, but we have to prove, I don't know, more rigorously. We're gonna suppose that we take a point with integer coordinates, so we take one of those black bullets, and we suppose this point belongs to this straight line. So it means that these two numbers, they satisfy this equation. So y0 is equal to q over p times x0. So this means that p times y0 equals q times x0. This equation implies that p divides this product q times x0, but we know that p and q are both odd primes, and those are different primes, so it means that GCD of those numbers is 1. It means that p cannot divide q, so the only possibility here is that p divides x0. And here comes the problem. This x0 is an integer coordinate here, 1, 2, 3, all the way up to the last possible element, which is strictly less than p over 2, and that is p minus 1 over 2. So this x0 belongs to this interval from 1 to p minus 1 over 2. But x0 is divisible by p, so it must be 0, p, 2p, or negative p, and so on and so forth, which is not possible according to this inequality. So we reached the contradiction. Now, since this blue diagonal splits our rectangle into two triangles, I'm gonna denote each triangle. So this will be denoted by triangle T1, and this triangle will be denoted by T2. And now here comes the main question. The main question is here: how many bullets are in this triangle T1 and in this triangle T2? By bullet, I mean this point with integer coordinates. To compute how many bullets are in T1, we just take each x and try to evaluate the number of bullets underneath this straight line. So in this example, if you take x equals 1, we have 0 bullets. If you take x equals 2, you have only 1 bullet. X equals 3, 2 bullets, and so on and so forth. So in general, we just fix some k, which is on x-axis, and it's between 1 and p minus 1 over 2. And now we have to compute the total amount of bullets on this red line. So we have to compute the number of bullets on this red line underneath the blue diagonal. So it means that we have to compute how many integers of y we have here. So if this is k, then this point, this one blue, corresponds to q over p times k, according how we define the straight line with this equation. So we need to compute how many y's, integral y's, do we have between 1 and this point, so between 1 and q over p times k. Now, how many integral y's do we have here? So how many bullets do we have here? Well, we just have to take this element q over p times k and take its integer part, which is the biggest possible one, such that it's less than q over p times k. So at this red line, we have totally integer part of q over p times k bullets. And this holds for any k between 1 and p minus 1 over 2. Thus, if I do the same procedure for any other k between 1 and p minus 1 over 2, and then I will sum up the total number of bullets, then this will be denoted by T1, and this T1 corresponds to the total amount of bullets in T1. So this is k equals 1, k equals 2, k equals 3, and so on and so forth. So we took all bullets on this triangle T1. With the almost similar fashion, you can prove that the total amount of bullets in this rectangle T2 is going to be this sum of integer part of p over q times g, where j runs from 1 to p minus 1 over 2, and this is denoted by T2. Well, let me just explain a little bit in detail. So this is your j. This time you pick any j from 1 to q minus 1 over 2, and then your question here is to compute the total amount of bullets that lie on this red line underneath this blue diagonal. So this time you compute the total amount of possible x, such that those are underneath this point. But we know that this line is given by this equation y equals q over p times x, and we want to find this x coordinate, so it's just p over q times y, and you plug y equals j right over here, you get that this point is equal to p over q times j. The total amount of bullets in this rectangle is just T1 plus T2, where T1 is this sum and T2 is this sum. This is only one hand how we can calculate the total amount of bullets inside this rectangle. There is other hand, however. Each bullet inside of this rectangle is represented by the following coordinates x0, y0, where x0 is an integer between 1 and p minus 1 over 2, and y0 is also an integer between 1 and q minus 1 over 2. And now here comes the combinatoric time. So how many x0 can we pick here? We have totally p minus 1 over 2 possible x's. And how many y0 do we have? Similarly, we have q minus 1 over 2. And we just have to multiply those numbers, and this number corresponds the total possible amount of those points x0, y0. So this is just the total amount of bullets inside of our rectangle. So it means that this T1 plus T2 is exactly the same as p minus 1 over 2 times q minus 1 over 2. Now, by preceding lemma, since p is an odd prime, Q is co-prime with P and also an odd number, then we can rewrite this Legendre symbol as -1 raised to the power of T1, where this T1 is just the sum of those integer parts. Likewise, we can rewrite Legendre symbol of P modulo Q as -1 raised to the power of T2, where T2 is this sum with those integer parts P over Q times J. Now finally we just multiply those Legendre symbols so that we have P mod Q and Q mod P. This is just -1 raised to the power of T1 times -1 raised to the power of T2, which is just -1 raised to the power of T1 plus T2. But this number is just the same as P minus 1 over 2 times Q minus 1 over 2. QED. So now before providing you an example, I would like to rewrite this equation with more details. But before, you should recall when this fraction is going to be either odd or even. So if you take this number s, which is congruent to 1 modulo 4, then this fraction is going to be even. However, if s is congruent to 3 modulo 4, then this fraction will be odd. So this will help us to examine this power. First, let's suppose that either P is congruent to 1 modulo 4 or Q is congruent to 1 modulo 4. So if P is congruent to 1 modulo 4, it means that this fraction is even. Even multiplied by anything is still even. But if Q is congruent to 1 modulo 4, then this fraction is going to be even times anything, which is still even. -1 to the even power leads to the number just 1. So the product of those Legendre symbol is 1. And this is possible when either this Legendre symbol and this Legendre symbol is just 1, or they are both -1. So it means immediately that those Legendre symbols has to be the same. So this Legendre symbol P mod Q and Legendre symbol Q mod P, they have to be the same. So it means that we can just flip this fraction when we have this case. The second case is when we have P is 3 modulo 4 and Q is 3 modulo 4 simultaneously. So it means that this fraction and this fraction, they are going to be odd. So we have -1 raised to the power of an odd number, which means that the product of those Legendre symbols is -1. So it means that this Legendre symbol and this, they must have those values. Either this one is 1 and this -1, or first one is -1 and the second is +1. So it just means that Legendre symbol of P modulo Q is the same as Legendre symbol of Q modulo P with negative sign. So again, we can flip this fraction, but this time we should add an extra minus sign. So let's try to compute this bad boy, Legendre symbol 79 modulo 83. Well, here's the main problem. Those numbers are kind of massive. And if you try to apply Euler's criterion, so this is going to be like 79 raised to the power of 83 minus 1 divided by 2, and in the world of modulo 83. Well, those numbers are really massive ones. It will be better just to quit mathematics than computing this. However, luckily, we have another law, the law of quadratic reciprocity, which simplifies a lot. Well, first, let me notice that 79 and 83 are both prime numbers. 79 is congruent to what in the world of modulo 4? Well, you can see that this 79 can be written as 76 plus 3. And this 76 is divisible by 4, so we are only left with just 3. Thus, 79 is going to be congruent to 3 modulo 4. The same question goes to 83. It's congruent to what? Well, 82 is divisible by 4 and plus extra 1, so this is going to be congruent to 1 modulo 4. So by preceding remark, this tells you that this Legendre symbol 79 modulo 83, this can be rewritten as Legendre symbol of, and you can just flip this fraction, so 83 modulo 79. And here plus sign, because we have at least one prime which is congruent to 1 modulo 4. And now let's notice that 83 is going to be congruent to 4 modulo 79. So this Legendre symbol can be written as Legendre symbol of 4 modulo 79. However, this 4 is nothing but 2 squared, and the Legendre symbol of any squared number is 1, so this is just 1. Now this is the end of the lecture, and I'm not going to furnish any exercises since we are not done yet.